I'm working currently at the University of Chile in Santiago, which is the capital in the middle of Chile. In this presentation, I'm going to talk about the CubeSat, about the science possibility, this type of technology, and the case of the SUCHAI program, which is a program that we are developing at the University of Chile, in which we are collaborating multiple projects with other institutions nationally as well and internationally. Okay, why Chile? Why do space research in Chile? First, we are very strange in terms of geography and location. We are a very long country, as Chile. So if we take the extension of Chile, we cover part of Canada, the whole US, and part of Mexico in terms of latitudes. So we cover multiple latitudes in the southern hemisphere. The other part, and the other interesting thing is that we are located in the southern hemisphere, where it's mostly water in the southern hemisphere. To have land and to cover multiple latitudes, it's very useful for doing space research. Also, we have a lot of different climates and different geographies and geophysics places due to the length of the country. So we have very cold weather, we have part of the Antarctica in the south, and also we have very dry climates in the north of Chile, which are very well known for the astronomy. We also have technology, very sophisticated and state-of-the-art technology, thanks to the astronomy. The astronomy is located mostly in the north of Chile, and as Eduardo Ibar and Eduardo Unda made a recollection of some of the projects that are being developed there, we have a lot of human capital, people that it's very knowledgeable also in technology. We are taking the opportunity of the nano satellite trend, which provides a fast and low cost development, and having or proposing rapid innovation cycles for testing technology in space. And also because of these ground facilities, we also can monitor and support space activity, in particular satellites and space stations research and collaboration. This is in this presentation, I'm going to talk about two main CubeSats, the SUCHAI 2 and SUCHAI 3, and some of the activities that we are doing with them. This is a multi institution and multidisciplinary collaboration between different institutions. Okay, and we have also different level of people collaborating on these, graduate students, engineers, space physics research, astronomers in collaboration to monitor light pollution from space, and satellite technology as well, and communication in particular. So what is the space program, that the strategy that we are developing? Okay, the first study that we are working on, and it's mainly the motivation for many of the other research that we are conducting with these satellites, is the study of the space environment. Okay, so we want to understand very well what are the conditions in the space, in particular with radiation, and in particular with temperature and radiance and multiple things. And one reason is because this technology, the technology used in CubeSats, it's very new. Okay? So it means that it's unknown what it's going to be the behavior in space. And we need to understand more or less this in order to see what are the possibilities that we can have in using this technology in space. So we started, we have been studying the space environment And also taking advantage that the CubeSats are low cost. So it means that we can have multiple points in space. So providing the opportunity to study the dynamics. So when you have just one satellite, you cannot resolve if the changes are spatial or temporal. So the opportunity of having more points in space can give you more information about the phenomenon or the phenomena that you are studying. In particular, why also studying space environment and sometimes also called the space weather topic. It's because Chile is also, in South America in general, it's well located to do this because it's there is the shield that protects our country, our planet. Sorry, it's based on the magnetic field of the Earth. The magnetic field it's a shield that protects from the particles that are coming from the sun constantly. Okay, so and these particles tends to keep trapped, okay, in the magnetic field, and because of that, we see certain phenomena like auroras in the poles, the northern and southern auroras, and also we have a radiation. Those trapped particles are known like radiation belts, and we have one which is external and the other one that is internal. Okay, the International Space Stations tends to be below the internal um, um, radiation belt. But anyway, in some portion, it passes through the radiation belt. And why is that? Because there are some places where the magnetic field is weaker. Okay, and that place is over South America. And what is the implication on that? Of that is that we get more particles at lower altitudes, and those particles could be damaging the satellites. These are the external radiation belt footprints on the map, and this is the internal radiation belt. This is mostly ions, and this is mostly electrons. Okay, so we can see that the electrons is more intense, usually in the southern hemisphere, and also then you have the South Atlantic anomaly, which it's over South America. The weakest point in the magnetic field is around it's over Brazil currently, but this maximum of particles or minimum in magnetic field was originally in the Atlantic Ocean. Okay. So the center, it's moving towards the west. If we follow this trend for the 2030, the maximum of the radiation particles and or the minimum in the magnetic field, it's going to be over Chile. So we were trying to understand this. We are trying to see what are the consequences of having this maximum of the Southern Atlantic anomaly over us. What is the impact in the GNSS sensitivity? GNSS is the GPS, the global position systems. And so the question is, what is the fact of having this anomaly over us? And also how can we complement the studies in space with ground-based instruments. So based on that, we started to work in our Sputnik, our first CubeSat, the SUCHAI. The SUCHAI-1 is a satellite that was conceived as a seed project. It was a technology demonstration to see if we can develop the satellite and the instruments inside of it. It was funded by the university, by the Faculty of Physical and Mathematical Sciences at the University of Chile. And the project is named Satellite of the University of Chile for Aerospace Investigation, with the acronym named SUCHAI, which emulates the word SUJAI, which means hope in one of the native languages in our country. So this project was carrying multiple systems, technology, antennas, antenna system. We were testing 3D printing materials for space. But in terms of the science, we were carrying a lightning probe, which is a system that measures the density of the particles that are charged in the ionosphere. Those charged particles are not coming from the sun, are coming from the atmosphere. The UV radiation, yeah, ionize the atmosphere in the top level. So we have particles that are there seated, charged, ions and electrons as well, that are affected by the electrons and ions that are penetrating through the magnetic field. So we were having a lightning probe that also carries a particle counter. So we can see what were the effects of the changes in the density of the charged particles compared to the particles that are being precipitating from the outside of the magnetosphere. And also we were carrying a camera that we are going to see what was the use for that in the coming picture. Okay, these are some of the results that we have been getting and processing with the SUCHAI 1. This project started in 2009 as a conception. We got the funding in 2011. After 3 years, more or less, of developing, we finished the CubeSat, and we were waiting for 3.5 years for the launch. We were scheduled in SpaceX in Falcon 9, and because at that time they were testing the landing procedure, we had to wait a lot of time. In the end, we moved to another provider, to PSLD from India, and we launched from India. Those are some images. So for this reason, we were having the camera next to the lightning probe, because this probe, the sphere, has to be released, and we were going to check if the sphere was outside and was released properly, which the image shows that. And we were able to take in this image, we can see that the particle counter, which is very tiny, was detecting the ions and electrons. Electrons were detected mainly during a storm, okay, solar storms, magnetic storms, and not during all the time. So here we can see July and August, we didn't have strong activities, and we can see different behavior during daytime and nighttime. The South Atlantic anomaly is moving in latitude compared to day and night, and we see the same behavior during periods of activity, but we see the electrons as well. And what we can do, we can combine with other systems. In particular, here we can see images built with total electron content, obtained with GPS stations around the world. So we can see here, for example, for the period of activity, one of the largest activities was in August 27th, and we can see that compared to August 3rd and September 6th, we get a very strong activity in the electrons, okay, and it's correlated with the strong activity of particles injected to Earth. Okay, so we are processing this, but we can combine this data from ground in Chile with data from space collected with our own instruments in space. This data was collected from the National Seismic Center data, and the data that is associated to that around the world, because they are sharing the seismic data from the GPS stations. Some results are related to the technology. In particular, we are developing the flight software, which is open and free to download and work, and has certain abilities to be tested on the fly. Okay, so you can be building the satellite and the CubeSat and testing these in a very agile way. And here are some results of publications. We have been studying the state of health of certain elements in space. As I mentioned, we are trying to understand what is the effect of the space environment in certain components and technology in a very deep and profound manner. So one of the key elements for us are the batteries. So what are the current missions that we are working on? We have 3 missions that are scheduled to be launched in 2022, early 2022, and these are the missions. The 3 missions are going to do similar demonstrations in terms of space physics research. So they are going to carry magnetometers, Lagnier probes, GNSS receivers or GPS receivers to measure total electron content from space, and particle counters as well, again. Okay. But this time we are going to study and evaluate some technology that we are going to be using, and later on I'm going to mention a little more about this, but it's the attitude system and communication system. The 3 of these satellites are going to be measuring the space environment, but because they are measuring the space environment, we can study what is the effect of the space environment over certain systems. In particular, one of the satellites is going to evaluate the effect over biological system, which is the Planetsat. SUCHAI 2 is going to evaluate an optical system, which is going to be used to monitor light pollution from space, and another one, the last one, for communication, Internet of Things platforms, LoRa in particular, from space. And also we are going to carry tiny satellites that are going to be deployed with magnetometers to increase the number of points in space to measure the magnetic field that allow us to measure as well, to determine currents in space. Sorry, I forgot to mention something. There is a plasma thruster that we are collaborating with the Commission of Nuclear Energy, the Chilean nuclear energy here in Chile, but this system is not being carried in these satellites in particular, but it's a project that we are developing in a collaborative manner with this institution. So the flight software, in this case, it has been extended to work and collaborate in constellations. So it's being automatized and add with artificial intelligence to enhance operation, production and operation in space in an autonomous way and based on task objectives. So we are being working in, as mentioned, in attitude estimation control systems, where we are working in reaction wheels and start trackers. Most of these systems are open hardware, open software, and also we are developing and working in the development and integration to cubesats of tiny, really tiny plasma propulsion systems to perform outstanding attitude control for multiple applications in astronomy, but also for optical communication system and radio communication system and interlinked satellite communication as well. This is the one of the system in the bottom here. I don't find my this is as an array of antennas with a hole in the middle. So in this place we can place cameras or lasers or system that can be that can be guided or supported in estimating the angle of arrival system using the radio platform. So in the SUCHAI 2, I'm going to mention some particularities. The SUCHAI 2, besides the the experiments for space, or the instruments for space, we are going to evaluate an optical system that could be useful for astronomy, but we are going to use it for quantify light pollution from space. This is a collaboration with multiple institutions, the light pollution and also the space weather. The space weather is being developed from the University of Chile in different faculty of science faculties, faculty of mathematical, physical and mathematical sciences at the University of Chile, and the Faculty of Science. The laboratory developing the satellites is the Space and Planetary Exploration Laboratory, in collaboration with the University of Santiago of Chile, and internationally with Embry-Riddle and the SAIL laboratory. These are the researchers working in particular in the space research area. And this is the project that is mainly finding the satellite and the construction of the satellite. Those are the projects that are being funding this project. The one part of this mission is the light pollution estimation from space. Okay, for that we need to pointing, so we need an attitude control system that is going to be evaluated in space, and we need to point to certain places. Okay, one of the places is going to be in Antofagasta, where we expect to calibrate the image and take images from that region to evaluate the performance of the camera and the pointing capabilities that we have. Here are the institutions that are collaborating in this project: the Universidad Valparaíso, Universidad de Antofagasta, Las Campanas Observatory, and a former researcher from Pontifical Catholic University of Chile and University of Chile again, and our lab. As you see here in the video, this is the system that I was mentioning, that with radio, we can guide a system that has the antenna. The system can recognize from where is the beacon coming, and we can help to support the guidance to certain region where we can do the calibration. Why we are doing this in particular? Because there are certain differences in the images that we are being taken with other satellites. In particular, these are taken with infrared images. The resolution in ground is not that good because they are too high to have a good resolution. But also with heat, what they expect or what they see, it's in other frequencies, in higher wavelength. So in particular here, we can focus in this region where we don't see in the 2016. And this might be due to a change in technology where the white LEDs are not being detected with the current system that we have in space to monitor the light pollution. So the camera, it's that selected and we are testing in space has not been in space before, but has an extended wavelength spectrum, and we can detect the bluish or white light that is coming from new LED system. The SUCHAI 3, it's going to have an IoT system, which is going to be evaluated in Internet of Things system, but also the space research and also the attitude system. So we are going to test that. But also we are going to have the same system that is pointing down and use it in SUCHAI 2 for finding the calibration side. It's going to be at the side of the telescope of the satellites. And with that, we can see if we can geolocate the femtosatellites that are going to be deployed in space to measure the currents in space. And also, because we have the whole, we are going to test if they might be useful for doing other measurements or interlinked satellites as well. This is for now for this presentation. I'm going to talk later on from the biological telescope, which is a little different, but for the moment, the SUCHAI 2 and SUCHAI 3, this is the presentation of those missions.